Greetings of the day, everyone. Today we are starting our lecture on computer organization and architecture, specifically focusing on the central processing unit. Central processing unit, general register organization. The CPU is the brain of the computer and is responsible for executing instructions. It consists of three major components: the arithmetic logic unit, control unit, and registers. Every task we perform on a computer, whether opening an app, playing a game, or browsing the internet, it involves CPU operations. The CPU processes data and instructions stored in memory and performs calculations or logical operations based on them. The key aspect of CPU performance is memory access. Memory operations take more time compared to processing. So using registers to store temporary data is faster and more efficient. In this lecture, we will discuss CPU organization, register operations, and how instructions are processed within the CPU. Now, introduction to Central Processing Unit. The Central Processing Unit is the brain of a computer. It is responsible for executing instructions, performing calculations, and managing the flow of data within a system. It is the most critical component in determining the speed and efficiency of a computer. Every operation, from basic arithmetic to complex data processing, depends on the CPU. The CPU consists of three major components which works together to execute instructions efficiently. These components are arithmetic logic unit, that is ALU, the control unit, that is CU, and the memory unit or registers. Each of these plays a vital role in ensuring the smooth execution of program. Now, talking about the functions of the CPU, the CPU performs a variety of functions dictated by the type of instructions incorporated in the computer. Some of the functions include fetching instruction, decoding instruction, executing instruction, and storing the result. Talking about the role of memory in CPU operation, memory plays a critical role in the operation of CPU. In programming, memory locations are needed for storing pointers, counters, return address, temporary results, and other essential data. Since accessing memory is time consuming, the CPU relies on registers to store intermediate values. Registers allow for faster data retrieval as they are directly connected to the processor via the common bus system. Since memory access is one of the most time-consuming operation in a computer, the use of registers significantly enhances CPU performance. Additionally, modern CPU incorporates cache memory, a small but high-speed memory that stores frequently used instructions and data. This further reduces the time required for memory access, leading to better performance. A registers-based CPU is a type of processor architecture where multiple registers are used to store temporary data during computation. This organization enhances processing speed and efficiency by reducing memory accesses, making it a preferred design for modern CPUs. Talking about the characteristics of register-based CPU, unlike accumulator-based CPUs, which rely on single accumulator for operations, registers-based CPUs utilize multiple registers to hold intermediate values and perform calculations efficiently. Since registers allow direct access to data, instructions do not require a memory access leading to shorter and faster execution of program. Registers-based architecture often use load and store operation, where most arithmetic and logical computations happen within registers rather than memory. Talking about the advantages of registers-based CPU, it provides shorter program size. The use of registers minimize the need for memory access, reducing the length of instructions and making programs more compact. Increased CPU efficiency, as more registers mean faster computations, as data retrieval occurs directly from the CPU rather than external memory. Talking about the disadvantages of registers-based CPU, additional memory accesses are required. Although registers improve execution speed, register spills occur when the number of registers is insufficient, forcing the CPU to save and retrieve data from memory. This can slow down the performance, particularly in systems with limited registers. Then dependency on efficient compilers. Registers-based architecture demands smart compiler design to optimize register allocation efficiently and effectively. Poor register allocation can lead to unnecessary memory operation, negating the benefits of having multiple registers. The general register organization in a CPU enables efficient execution by allowing registers to communicate directly with the ALU via data, address, and control buses. Let's explore how registers interact with the ALU using buses and delve into the operation of the memory stack. This diagram represents a detailed data path of a register-based central processing unit. This type of CPU relies on registers for storing and processing data during computation. This diagram illustrates the fundamental components and how they interact executing the instruction. Talking about the components of the CPU data path, registers R1 to R7. The CPU contains multiple registers R1 to R7, which are small, fast storage location used for temporary data storage during operations. These registers hold operands for arithmetic and logic operations and intermediate results. The clock signal synchronizes data movement within the CPU. Every operation occurs in discrete time interval dictated by the clock pulses. Two multiplexers are used to select data for the registers. The select A and select B control signals determine which registers data are sent to the A bus and B bus respectively. The multiplexers help in selecting different registers dynamically based on instruction requirements. A bus and B bus act as highways for data transfer between the registers and the ALU. The bus A and bus B carry the selected values from the registers to the ALU for computation. The ALU is responsible for performing arithmetic operation, for example, addition, subtraction, multiplication, etc., and logical operation, for example, AND, OR, XOR, etc. The operation performed is determined by the OPR, that is operation code, control signals. The 3x8 decoder is used to enable one of the 7 registers for loading the data. The select D, that is select destination, control signal determines which register receives the result of an ALU operation. Load signal ensures that the selected register captures and stores the result from the ALU at the right moment. Now talking about the control world. The control word consists of total 4 fields. Select A is of 3 bits. It selects the first operand register for the ALU. Select B of 3 bits selects the second operand register for the ALU. Select D of 3 bits selects the destination register to store the ALU result. OPR of 5 bits determines the ALU operation, that is addition, subtraction, and or etc. Now, talking about the working of the CPU data path, the control unit generates select A, select B, and OPR signals to choose two registers and the desired operation. The selected registers send their data through A bus and B bus to the ALU. The ALU performs the operation, specified the OPR signal. The result from the ALU is sent back to the register selected by select D. The load signal ensures that the correct register captures the result. The cycle repeats for each instruction, enabling complex computations. Now, the importance of this data path in CPU design is efficient data handling, modular control, high-speed execution, and scalability. This detailed data path representation showcases how a register-based CPU processes instructions efficiently. The instruction, or you can say the interaction of registers, buses, multiplexers, and the ALU allows the execution of arithmetic and logic operation in a structured manner. Such a design is crucial for modern processors, ensuring speed, accuracy, and efficient resource utilization in computing tasks. Here we can see the example of one micro operation that says add the content of R2 and R3 and put it into R1 register. So micro operations are fundamental operations that occur within the CPU to execute an instruction. These operations involve transferring data between registers, performing arithmetic or logical calculations, and controlling the flow of data within the system. One such micro operation is shown here, which represent the addition of content of register R2 and R3 and storing the result in R1. To perform this operation, the control unit must generate appropriate control signal to direct data flow and processing within the system. So a control word is generated, which is a set of control signals represented as a binary word. Each bit in the control word represents or corresponds to a specific control signal that governs different operations within the CPU. For R2 and R3 component addition and storing it to R1, the control word will include the bits for select A, select B, OPR, and select D to coordinate the required data flow. This example illustrates how micro operations utilize multiplexers, buses, ALU operations, and destination decoders to execute an arithmetic instructions efficiently within a CPU. So, in this lecture, we learned about the CPU, its structure, and how it processes instructions using registers and micro operations. The key takeaway is that registers improve efficiency by reducing memory access time, and the CPU uses a bus system to transfer data efficiently. If you have any questions, feel free to ask. Happy learning.